Hello everybody, we're getting ready to do lesson 9.2 part 3 of classwork of pre-calculus math today. And for today's classwork you'll have 8 points that will go into your notebook guide, and then 10 points on your classwork sheet. Students, put your name, date, period. Homeschoolers and onliners, put your due date here. And then today's bell work, teachers, students, here's today's bell work. In exercises, find the sum. So find the sum of these different summations, students. Give you about 4 minutes to do that. Teachers, pause your video for 4 minutes and see you then. Okay, welcome back everybody for the solutions for today's bell work. We have an upper limit here at 6, and we start at 0 here, 3n. So 3n actually here from when we start at 0 and then we go up to 6, we get this amount here for our summation. And then down here for this one, upper limit 10, n starts at 1, and then 4 times 3 over 4 to the n minus 1. That summation will equal 15.099. Into today's lesson, part 3, eccentricity. I know this was in part 2 of your classwork. Some of your examples and your guided practice and independent practice talked about eccentricity. Well, here it is here, eccentricity. One of the reasons it was difficult for early astronomers to detect that the orbits of the planets are ellipses is that the foci of the planetary orbits are relatively close to their centers, and so the orbits are nearly circular. To measure the ovalness of an ellipse, you can use the concept of eccentricity. So the definition of eccentricity, the eccentricity E of an ellipse is given by the ratio E equals C over A. So there is your eccentricity formula. So once we know our C and our A, note that 0 is less than E is less than 1 for every ellipse. To see how this ratio is used to describe the shape of an ellipse, note that because the foci of an ellipse are located along the major axes between the vertices and the center, it follows that 0 is less than C is less than A. Like here's your example here, here's your foci here, here's your C distance here, here's your C distance there. Our eccentricity will be our C, our length of C over A in this situation here. So our A would be this amount here. Here is your A distance here from your center to your vertices. For an ellipse that is nearly circular, the foci are close to the center, and the ratio C divided by A is close to 0. Okay, so we know that. On the other hand, for an elongated ellipse, the foci are close to the vertices, and the ratio C over A is close to 1. So in this situation here, an elongated ellipse, so the foci are close, or here's your foci out here, E is close to 1. So when it's close to 1, it seems like your foci will be spread further apart for that situation to happen. The orbit of the moon has an eccentricity of E equals 0.0549. So it's pretty circular of an orbit around the Earth. So that it would be your eccentricity value for the orbit of the moon. And the eccentricities of 8 planetary orbits are as follows. So we get an eccentricity value for these planets here. Here they are here. So the closer they are to 0, the more circular they are. So this one here, the Neptune orbit, would be I'm sorry, the closer they are to 0, the more of an elliptical orbit they have. That's right. And like Mercury would have more of a round orbit. And then this one here is very Venus, the orbit of Venus is very elliptical. And see 0.05 Saturn, so they're close, 0.09. So these are very elliptical, these are elliptical, these are less elliptical. And then this is the closest one to being round, would be Mercury. And that is your part 3, 9.2. Pre-calculus lesson part 3 classwork. If you need classwork sheets, homework sheets, note-taking guides, email me animatedpowerpointmathvideo@AOL.com. Thank you.